Hello guys, welcome to your own clinical YouTube channel. So today we'll be discussing regarding fixed principle and its implication used in cardiac output measurement. So let us consider a question you must be facing in your entrance examinations, like calculate the cardiac output of a patient so and so from the following hemodynamic parameters like weight, hemoglobin, oxygen saturation, PaO2, PaCO2, SaO2, SpO2, and PbO2 is given. Okay, so let us understand. So we will be calculating the cardiac output using Fick's principle. So what is Fick's principle? So it is basically the conservation of mass. This principle relies on the basic principle of conservation of mass, and it says total uptake of a substance by our body or by a tissue or organ is equals to the product of blood flow to the tissue or organ and the arterial and venous concentration difference of the substance. Okay, so basically this principle is nothing but just a corollary of conservation of mass. Okay, so let us understand by an example. Let us consider our body or tissue, and there is an arterial supply and a venous drainage, right? So if we consider we are taking the oxygen from the arterial sample, utilizing the oxygen and returning some oxygen via venous sample, and if we calculate the oxygen content of arterial blood, oxygen content of the venous blood and differentiate it, we will be getting the oxygen consumption by our body or by the tissue, right? Are you getting the concept? So now we will be calculating the oxygen content of an arterial sample or venous sample, and upon differentiation we will be getting the oxygen consumption of the body. So we will be getting the venous oxygen content, venous oxygen sample via mixed venous sample from a PA catheter, or we will be taking the sample from pulmonary artery, which will be called mixed venous sampling. And for the arterial sample, we will be simply using arterial blood gas analysis, from which we will be getting the values accordingly. Okay. So from the formula we got oxygen consumption is equals to arterial oxygen content minus venous oxygen content into flow or the cardiac output. Okay, and in this formula oxygen consumption is expressed as ml per minute, which is termed as VO2. Okay, the cardiac output is expressed in liter per minute, then arterial oxygen content and venous oxygen content. Okay, from this equation, if we take cardiac output, becomes venous which becomes our oxygen consumption per unit time divided by arterial and venous oxygen content difference. So now we'll be calculating the oxygen content of the arterial and the venous sample by using a standard formula. As we know, oxygen is there in two forms. One is bound to hemoglobin, another is dissolved form, right? So it is 1.36 into hemoglobin concentration into hemoglobin oxygen saturation plus the dissolved form, which is 0.003 into PaO2. Same goes for the venous blood, what is 1.36 into hemoglobin into oxygen saturation of hemoglobin in the venous blood plus 0.003 into PvO2. For calculation purpose, you can ignore the dissolved part because it contributes to less than 1% of the total oxygen content. Okay. For calculation in the arterial sample, it is 1.36 into 10 into 99 as given in our question, 99%, which is 0.9. So upon calculating it for the venous sample, we get 1.36 into 10 into 60%, which is 0.6. So we get a value of 13.5 for arterial sample and it is 8.2 for the venous sample, right? And the units are ml of oxygen per deciliter. So remember it. For further calculation purpose, we will be converting into this ml per deciliter into ml per liter, because our cardiac output calculation is liter per minute. Okay, so we need to modify these units by calculating, by multiplying these values with 10, so that we'll be converting this ml per deciliter into ml per liter. Okay, hope we are clear till now. So again, VO2 or oxygen consumption of our body at resting phase per unit time, which is equals to 3.5 ml per kg per minute. So for a 60 to 70 kg adult, we can calculate it as around 250 ml per minute, and we'll be using this standard value for our simplistic calculation. So cardiac output equals to VO2 minus arterial and venous oxygen content difference. So which is equals to 250 minus the values we have calculated previously, it is 13.5 minus 8.2, and we remember we need to modify these units to ml per liter. So we will be multiplying this 13.5 minus 8.2 value by 10. Okay, so it becomes 250 divided by 13.5 minus 8.2 whole into 10. So upon calculation, we get a value of around 4.5 or 4.6 liter per minute. So this way we got our cardiac output by using Fick's principle. Understood? Okay. So now what is Hofner's constant? HUF-NER. Sometimes it is also written as HAUF-NER, Hofner's constant, or HUF-NER, Hofner's constant, interchangeably. So this is basically the oxygen carrying capacity of our hemoglobin. Okay, and its theoretical value is around 1.39, but in experimental models we got the value to be 1.31 to 1.37 in some models. Okay, so for calculation purpose we take it as 1.36 or some take it as 1.34. Okay, so hope you are clear regarding this concept of Fick's principle. Keep learning. Thank you.